All right, so 12.5, arc length and curvature. Okay, so we've talked about arc length several times over the course of the year. We're just going to we're going to extend what we know about arc length for parametric equations to vector value functions, and then we're going to use arc length to come up with this idea of curvature. So if we had parametric equations, and we're talking just in the plane, where we had x equals some function of t, x of t, and y is some other function of t. So these were our parametric equations. On some interval from a to b, we said that the arc length on that interval for these parametric equations, we said s was our integral from a to b, whatever our interval was, of the square root of x prime of t squared plus y prime of t squared. And that was how we calculated arc length for parametric equations. So if we let our curve be represented by a vector valued function in space, so we're going to say in space, we have a position vector. R of t is this vector valued function, x of ti plus y of t j plus z of t k. Then we can say that the arc length on our interval using the same idea, and I'm going to say I'm going to say from t equals a to t equals b is, and we have the same expression. We just have another quantity in our radical. So we have the integral from a to b, the square root, and I'm going to drop the t's here. We know that our component function depend on t. I'm going to say x prime squared plus y prime squared plus z prime squared dt. And we know that each of these is a function of t. Well, what is another way of writing this radical, square root of x prime squared plus y prime squared plus z prime squared? This is the magnitude of r prime. So the magnitude of r prime of t equals this radical. So the magnitude of r prime of t equals this quantity, x prime, and I'm going to drop the t dependence here, plus y prime squared plus z prime squared. So we can say in space, for a vector valued function, s is the integral from a to b of the magnitude of r prime of t dt. And our assumption here is that r of t is smooth on our interval. So this is how we're going to work with arc length when we're working with a vector value function. Arc length is just the integral over our interval of the magnitude of r prime. And if we remember when we worked with arc length before, what often is the case when we're trying to find arc length? Because we have an integral and we have this radical and these things inside. What's that? Trig sub, or they just turn out to be difficult integrals, or Mathematica, right? Mathematica says so. Okay. So we've done a lot of examples calculating arc length. What this is really no different. We just have this extra component in our radical. Same idea. Often arc length integrals turn out to be difficult to evaluate. We end up using our calculator, using a numerical technique, looking up things in tables, that kind of thing. So this is exactly the same as what we've done in the past when we're working with arc length. It often leads to kind of messy integration. I'm not going to do an example of calculating arc length. We've done a lot of arc length problems. There's really nothing different here. We're just using this expression as our integrand when we're finding arc length. So same thing we've done several times before. But what we're going to do is use this idea of arc length to come up with a way to quantify the curvature of a curve. So let's go through the process of working towards that. So let's look. We have this expression for arc length. Let's look at a curve in space. I'm going to sketch a curve in space here, and we're going to talk a little bit about the arc length. So here are my axes, and we have some curve here. So here's our curve, and we're going to say this is our R of t, curve represented by R of t. And we're going to go along this curve from t equals a to some arbitrary time t. So from here to here is our arc length. So what we're going to do is first we need to come to an agreement here. Let's let arc length be a function of time. Let's think of the arc length as a function of time. So we're going to say let s equal some function of time. Can we agree that at any time t, if we're letting the arc length vary with time, at any particular time t, that arc length is going to define a unique point on that curve? Does that make sense? So we're saying that we're going to let arc length vary with time. If we define a particular arc length, that tells us exactly where we are along that curve. So we have an expression for the arc length. We can let it be a function of time. So the arc length is going to define a point on the curve. So S of t defines a point on the curve. So if say I have some function for the arc length, if I plug in a different time, doesn't that take me to a different place on the curve? So we've traveled, 25 units along the curve. At a different time, we've traveled 30 units along the curve. So we're just saying we've gone that far along the curve. So rather than x, y, and z, we're saying we're 72 units along the curve. That's all we're saying. We would have to. So we're saying we're starting. We have some starting time. We're going to define this point as t equals 0, and then from there, any point after that, we have a unique point on the curve. All right. So we're going to say using our expression for the arc length, s of t, our arc length as a function of t, is going to be the integral from a to t, from where we start, from some point to some arbitrary time t, of r prime, and then u is just my dummy variable for integration. R prime of u du. So this is going to be my arc length function. So we're going to say that s of t, and we're making this we're defining this here. S of t, this expression that we have, the integral from a to t, some starting point to arbitrary time of r prime of u magnitude du, and we said that is equal to, and I'm just going to expand this out, this big square root, this big radical, x prime of u squared plus y prime of u squared plus z prime of u squared du. This is our arc length function. So we're defining this as our arc length function. And we're going to say that s is the arc length parameter. So this function, this integral, is our arc length function, and we say s is the arc length parameter. This arc length parameter is going to be very important towards the end of the semester. We're going to use this arc length parameter quite a bit. What this does is gives us a way to parameterize the curve with respect to the arc length. So we can use the arc length as a parameter for our curve, and this lets us do a lot of different things. And like we said before, each value of s determines a point on the curve, so we can let s be a parameter and parameterize our curve in terms of the arc length. And we'll talk about why this is important in just a little bit. All right, so we said since s of t is this integral from a to b of r prime of u, and I said this was not a to b but a to t, since we've given it a time dependence, r prime of u du. What does the fundamental theorem of calculus tell us about this? What can we figure out from this relationship using the fundamental theorem of calculus? Not even thinking about quantities, but what does the fundamental theorem of calculus tell us the relationship between these two is? What else can we figure out about this relationship? What happens if we take the derivative of both sides? Fundamental theorem of calculus says, and that that would be an acceptable line in your proof. Fundamental theorem of calculus says. You can't say Mathematica says, but you can say fundamental. Fundamental theorem of calculus says that, and I'm going to write ds dt equals, and what is it? What did you say? The magnitude of r prime. So what this is saying is the rate of change of arc length and I'm going to say with respect to time is, what is the magnitude of r prime? What do we call that? No, not even the expression. What name do we give that? The speed. The rate of change of the arc length with respect to time is the speed of this moving point along our curve. So the rate of change of arc length with respect to time is the speed. This is going to be an important quantity in just a second. So we've come up with this idea of defining this arc length function. We have this arc length parameter s. We're saying it's a function of time. The rate of change of the arc length with respect to time is the speed of our moving function. We are going to use this arc length parameter to come up with this idea of quantifying the curvature of a curve. So what we're building up to is a way to quantify the curvature of a curve at any particular time t. So let's think for a second about curvature. Intuitively, when we think of curvature, what are we talking about? So it has, Mehmet says it has to do with the second derivative. It has to do with the acceleration. The acceleration, r double prime, is what tells us how much the curve is changing direction, right? So even thinking more geometrically, what are we talking about when we're talking about curvature? What's that? Concavity. Any other words come to mind? What's our most basic curved shape that we use? A circle. So we think of it has to do with something moving in a circle. And what do we think of when we think of circles? What are basic things that have to do with circles? A radius. So curvature, it might have something to do with some kind of radius. So let's look at a couple of pictures and let's try to pin this down a little closer, and then we'll use our arc length function. So let me draw two circles, and so there's one, and there's the other. Which one is more curved? The bigger one or the smaller one? The smaller one is more curved. So we think of this as having more curvature. And this one is having less curvature. The bigger the circle, the closer the circle is to kind of a straight line. So intuitively, how should the curvature and the radius be related? What's that? Small radius means more curvature. So we should have some kind of inverse relationship between the radius and the curvature, right? So we think that the curvature and the radius should be inversely proportional. All right. Let's draw a curve now. Rather than a circle, let's draw some curve. So here's our curve. And we're looking at this we're traveling along this curve from point A to point B. So in order to come up with this idea of curvature, we're trying to quantify this. We want some kind of thing that we can quantify as the curvature. So as we're moving along this curve, what can we say is changing? What quantities do we know about that is changing as we move from point A to point B? The angle of the tangent line. Okay, so let's the direction is changing. So when that says it has to do with the tangent vector, right? So let me draw another picture. And that's got a good intuition about what we're doing here today. So here's A, and here's B. And I'm going to draw our unit tangent vector. I'm going to draw several unit tangent vectors as we're moving along from point A to point B. And just looking at this curve, where would we guess? Where should the curvature be higher? Near point A or near point B? Near point B, right? It's turning more there. So let me draw in some unit tangent vectors. So here's a unit tangent vector, and this is just an approximation. That one was not very good. So this one should be like so. I don't know why I didn't get an arrow on that one. So there are my unit tangent vectors. So we're saying that, so what is changing, what's changing here with respect to we usually want to quantify things with respect to time. So as we move along from point A to point B, the rate at which the direction changes. So and going even a little more basic, the quantity that's changing is our unit tangent vector, right? It's changing direction. Our unit tangent vector is changing direction. It's changing direction more rapidly near point B than it is near point A. So where the curvature is higher, our tangent vector is changing more rapidly. So we're going to define, and in math we love when we can define things, because as long as our definition makes sense, we say this is what it is. So we're going to define the curvature using this as motivation. And we call the curvature K, as K is going to be the magnitude of the unit tangent vector, the rate of change of the unit tangent vector with respect to the arc length. So we're using our arc length as our parameter, and we're going to say that this is the magnitude of T prime of S. And this is for a smooth curve given by a vector valued function of S. So we're parameterizing our curve with respect to the arc length. And we said we thought that the radius and the curvature should be inversely proportional. So we're just going to define the radius of curvature. Is 1 over K. So our radius of curvature is just the inverse of our curvature. Now the reason that we choose S, the arc length, as our parameter is this ensures us that the curvature is independent of the parameterization. So if we parameterize, depending on how we choose our parameter of our curve, if we said that the curvature was a rate of change of the tangent vector with respect to time, we'd get a quantity for the curvature. But if we said if we parameterize our curve in terms of some other parameter, then we would come up with some different quantity for the curvature. So by defining the curvature as a rate of change of the tangent vector with respect to the arc length, we eliminate the effect of the parameterization on our curvature. So our curvature should be independent of the parameterization. It should be a property of the curve, not a property of the parameter. So that's why we use curvature in terms of the arc length parameter. So we're defining the curvature as the rate of change of the tangent vector with respect to the arc length along the curve. Now, just looking at this, what would you guess would be a problem with, or a difficulty, not a problem, a difficulty with this definition of the curvature? Yeah, our vector value function has to be parameterized in terms of the arc length. And have we done anything with parameterizing a curve in terms of the arc length? No. So usually we want to calculate the curvature with respect to our original parameter. So let's look at how we actually calculate our curvature. This is our definition. We want to be able to calculate. So we want to put this in terms of our original parameter. So we want K in terms of our original parameter. So that's what we're looking for now. And we have some nice quantities that we can use to do this. So we defined K as the magnitude of dt ds. We're going to use the chain rule and say that the magnitude of dt ds equals the magnitude of dt dt times the little t ds. And I'm going to write this as a fraction. So our curvature is rate of change of our tangent vector with respect to time divided by the SDT. What is our numerator here? What is the derivative of our unit tangent vector with respect to time? How can we rewrite that? Just t prime. And what did we say is the SDT? That's the magnitude of our prime. So K, finally, is the magnitude of t prime divided by the magnitude of r prime. Or closer, we could calculate with this, but there's another easier way. We said previously that a sub n, our normal component of acceleration, which we talked about earlier, that we thought that the curvature should have something to do with our normal component of acceleration. A sub n is the magnitude, we said magnitude of v times the magnitude of t prime. We said that was equal to v cross a magnitude over the length of v. If I manipulate this, I'm just going to divide by the magnitude of v, then I get t prime, magnitude of t prime. And I'm going to write this in terms of r and r prime. Magnitude of t prime is r prime cross r double prime over, and we have the magnitude, over r prime magnitude squared. And now I'm going to substitute this quantity for t prime here. So finally we get, this is the quantity that we're usually going to calculate with. The curvature is the magnitude of r prime cross r double prime divided by r prime to the third. This formula is usually going to be the easiest to calculate with to find the curvature. So this is how we can find the curvature of a curve when it's parameterized with our normal parameter t. So now we have a way to quantify the curvature of a curve. How curvy it is, right, right. And what's that? Well, these are all magnitudes. So our curvature is just going to be a scalar. So our curvature would be 10. And then our radius would be 1/10. Well, let's see. I guess the units, so if we define the radius of curvature as the inverse of the, so it'd be inverse, so it'd be 1 over meters, or per meter. It would be, we could get 10 per meter. 10 per meter. And our radius would then, when we take the inverse, we'd get our radius in meters. So this gives us a way to quantify the curvature of a curve. Yeah, the radius of curvature, r equals 1 over k. A large curvature means a small radius. A small curvature would mean a large radius. All right, I probably don't have time to go through an example of calculating. It's not difficult to calculate. We're just calculating with cross products and magnitudes. We should, on Friday, we should have a little time if we need to see some examples. I wanted to talk about what happens if we have our curve defined in rectangular coordinates. How we find our curvature in rectangular coordinates, really quickly. So is everybody good with this quantity for curvature and how we came about this quantity? All right. So the idea to me that we're talking about the rate of change of this tangent vector with respect to the arc length, and when we're dealing with this arc length, we're dealing with the geometric properties of the curve. So we're kind of applying calculus to geometry, and to me that's really kind of a fascinating idea. And the idea of quantifying curvature is just kind of a cool idea. Anyway, in rectangular coordinates, we let's say we have y equals f of x. So we're in a plane. We have y equals f of x. We're going to let x be the parameter. So we're just going to say our parametric equation for our curve. We're going to say r of t, or we're going to let r be a function of x, is going to be xi plus f of x j, and we're going to say plus 0k. And then our prime is going to be I plus F prime J. And the magnitude and R double prime. Sorry, let's do R double prime. R double prime is just going to be F double prime J. I'm just calculating all the quantities we need for our curvature. The magnitude of R prime is the square root of 1 plus F prime squared. So we're just going to use these quantities to calculate our curvature. This would, yeah, that's the arc length in rectangular coordinates. So we're kind of made a nice little connection there. So if we integrated this, we'd be finding the arc length in rectangular coordinates. So nice catch. So we're going to calculate for our curvature. We need R prime cross R double prime. So we get the quantity ijk. We're taking this determinant 1, F prime 0, 0, F double prime 0. When we do that cross product, it comes out to be F double prime K. And the magnitude of R prime cross R double prime is just the magnitude of F double prime. And then we just substitute all these quantities into our expression for curvature. So our curvature in rectangular coordinates is going to be the magnitude of F double prime of X over, I'll write it this way, 1 plus F prime squared to the 3/2. So this is how we would calculate, how we would compute our curvature if we have a curve in the plane defined in rectangular coordinates. Because when we do this cross product, it comes out to be F double prime K hat is our vector, and then when we take the magnitude of that, it's just the magnitude of that vector, which is just the magnitude of F double prime. It would just be the square root of F double prime squared, which is the absolute value of F double prime. So this is how we're going to calculate curvature in rectangular coordinates. Questions? So we only ended up with 2 formulas, but we kind of covered a lot of ground to get to those 2 formulas. We'll work on Friday a little bit more with curvature and radius of curvature, and we'll get to talk about this interesting idea called the osculating circle. And I have some nice animations that go with that. All right. Homework. There you go.